Okay, this is video about 9.8 related to intervals of convergence. So you need to remember back when we first introduced Taylor polynomials and we looked at the graph of the sine function. And the first thing I had you do was to write an equation of a tangent line. And then we looked to see how close the tangent line was to the curve sine of x. But then I had you put in this random polynomial, the x minus x cubed over 3 factorial. And then we looked at the graph and we saw that that particular graph was very similar to the sine function for a certain interval of time. And then we kind of expanded it to see how close we could get that polynomial to fit the sine function for even longer amounts of time or longer space of an interval. So we discovered that the polynomial was accurate only for a short interval. So on the one that you're looking at right now, it was centered at 0 because that's where we first found the tangent line. And if you just look at this, you can see the curve is the same from this first point all the way over to the second point. And so just as far as vocabulary, what we would say is the distance from the center all the way out to the point where it remains that the cubic function is still the same as the sine function, and then it starts to veer away. We would call that the interval of convergence. So that means you can go to the right that many units, you can go to the left that many units, and that is how long the polynomial will remain accurate for the sine function. And then, again, just as a matter of vocabulary, the entire interval, so from the negative side to the positive side, is called the interval of convergence. And so by convergence, we mean that's how long that the polynomial will remain accurate in predicting the particular function, in this case, predicting the sine function. So there's 3 possibilities of what might happen as far as related to this vocabulary. It might be that we find that the radius of convergence is 0. Well, think about it. If the radius of convergence is 0, that means it's not going to be accurate if you move away from the center, going to the left or to the right. It's not going to be accurate anymore. So if the radius of convergence is 0, then we say that the series converges only at the center. It doesn't have a whole interval. It just is the same at that one center point. However, if we find that the radius of convergence is infinity, that means that from the center you could go forever to the right and the polynomial would fit the curve, and forever to the left and the polynomial would fit the curve. So essentially the polynomial is the curve no matter how far you go out. So if we find that the radius is infinity, then that means that the series converges for all x, right, from negative infinity to positive infinity. But if we find that the radius of convergence is a finite constant, a specific number, then that means that the series converges for just a specific interval. So for example, on this one, if we find that the radius of convergence is 2, then that means if you go 2 to the right of the center at 0 and 2 to the left of the center at 0, the entire radius of convergence would be from -2 to +2. So that's what this interval up here means. From the center minus the radius to the center plus the radius would be the interval of convergence. So now we need to talk about, all right, well, how do we find what is the radius? Is it 0? Is it infinity? Or is it some specific constant? So there's 2 different things, 2 different kinds of series that we'll look at. If you recognize that it's a geometric series, right? It fits the geometric form. You have the a times r to the n. Well, first thing we have to do is always decide where is it centered. We know this one is centered at 0 because there's just an x here. If it had been centered at 2, there would be an x minus 2. Or if it were centered at 5, there would be an x minus 5. All right, so we know it's centered at 0. And we know that for a geometric series, it will converge if the absolute value of r is less than 1. Well, remember the r in this series is the x over 2. So essentially we're saying if the absolute value of x over 2 is less than 1, then we know the series converges. So you could do some guess and check, but let's just solve this equation. So if the absolute value of x over 2 is less than 1, we could write that as an equation. We could say x over 2 has to be between -1 and 1. And it might be that when you first learned how to solve this kind of an inequality, it might be that you learn, oh, you should write two equations. You should say either x over 2 is less than 1, or you would say x over 2 is greater than -1. But I think it's smarter to solve for what we're doing is let's write these together as one equation, because if x over 2 is less than 1, that would be what we have right here on the right side. But if x over 2 is greater than -1, that's what we have written right here. So we're just going to write it as one line and then solve it that way. So if I finish solving this, if I want to get the x by itself, I could multiply both sides by 2, and so I'm going to have that x is between -2 and 2. Well, if my interval is from -2 to 2, and I know this was centered at 0, that means that the radius is 2, because I went 2 to the right of 0 and 2 to the left of 0. And so my interval right now is -2 to 2. Well, I just have the less than. I don't know, I didn't say equal to. On a geometric series, I don't need to consider the endpoints, because remember, a geometric only converges if the r is less than 1, not equal to 1. If the r is equal to 1, it's a diverge. So in this case, for a geometric, there's no need to check the endpoints. Once I solve my equation, then I have my interval. Okay, for all other types of series, we're going to use the ratio test. And this is the one we're going to spend some time on. This is the one that's like that 4 or 5 point question on a free response. All right, so let's say we have this series. It's obviously not geometric because it's not a times r to the n. So we want to find the radius and the interval of convergence. So first of all, where is this one centered? Well, I see the x minus 5, so that's how I know it's centered at 5. So I'm just going to write that down, keep that in mind. And so like we said a minute ago, we're going to use the ratio test. Make sure when you set up your ratio test, you actually show that it's the limit as n approaches infinity. Make sure you show the absolute value. All of that's a part of the ratio test. Make sure you show that you're having the n plus 1 term, and then you can either say that you're going to multiply by the reciprocal of the n term, or the way we first talked about, we said it's the ratio of the n plus 1 term over the n term, but it's fine to go straight to this step. Okay, so that's the first point. And then we start to simplify. Well, I can tell that the x minus 5s are going to cancel, and it's going to leave me with an x minus 5 on top. I look at the 2's, and I can tell that that 2 to the n on top is going to cancel with that 2 to the n plus 1. It's going to leave me a 2 on the bottom. So what I have left is the limit as n approaches infinity. I have n on top. I have the n plus 1 on bottom. But also on top, I have the x minus 5, and I have the 2 on the bottom. So keep in mind, this is the limit as n approaches infinity. It's not a limit about x. So the limit as n approaches infinity of this first part, if you think about comparing the degree of the top and the bottom, is just going to equal 1. So if this limit is just 1, and this is separate from what I'm plugging infinity in for, then this whole thing just equals x minus 5 over 2, well, absolute value. And by the ratio test, the limit, the answer to the limit, which is this absolute value, has to be less than 1 in order for the series to converge. So I need to solve this equation in order to find out what that interval is where the series is going to converge. So go ahead and write it as a betweenness equation, right? X minus 5 over 2 is between -1 and 1. Solve for x, right? Multiply by 2. At this point, I know my radius of convergence is 2, because remember, it was centered at 5, and I have my x minus 5 in the middle. And this says, hey, I'm going to go 2 to the right, and I'm going to go 2 to the left. If you don't recognize that there, it's no problem. Just go on and solve for x. And if we solve for x, we're going to get that x is between 3 and 7. So think about it. If it's centered at 5, doesn't that mean the radius of convergence must have been 2? Okay, so this is my preliminary interval. But for the ratio test, I need to check the endpoints because remember, for for the ratio test, the answer has to be less than 1 in order to be a converge. If that answer is more than 1, then it's a diverge. But what if it equals 1? Remember, on the ratio test, if it equals 1, then it's inconclusive. So that means it might converge at 3 and it might converge at 7. We don't know. So that's why we have to check the endpoints. Okay, and the way we check it is I'm going to start by checking x equals 3, plug in a 3 up into the original series in place of x. So I'm going to rewrite that series, but in place of the x, I'm going to put in a 3. So instead of x minus 5 to the n, I've got negative 2 to the n. Okay, and if I start simplifying, now I'm going to think of this x minus 2 as, I'm going to separate it, and not x minus 2, the negative 2. I'm going to think of it as a negative 1 to the n being multiplied, say negative 1 to the n being multiplied by 2 to the n. And the reason I'm going to do that is because that way I can combine that negative 1 to the n. If I combine that with this negative 1 term, right, if I add my exponents, it's going to become negative 1 to the 2n plus 1. But if I look at it that way, then I can cancel the 2 to the n's that are on the top and the bottom. And so what I have left is just an n on the bottom. And if you notice this negative 1 to the 2n plus 1, well, won't 2n plus 1 always be an odd number? And if 2n plus 1 is odd, negative 1 to any odd number is just negative 1. So essentially, this series is simply negative 1 over n. Now, that's not an alternating. That's not alternating at all. It's not like it's positive and then negative. It is negative all the time. Well, isn't that just a harmonic series? I mean, yeah, 1 over n, negative 1 over n, same thing. And we know that a harmonic series diverges. So what that means is we are not going to include 3 in the interval. But I still need to check x equals 7. So do the same thing. Plug 7 in for x. And so instead of x minus 5, we're going to have 2 to the n. So on this one, I can see the 2 to the n's cancel. And what I have left is that negative 1 to the n plus 1. Well, that is alternating, right? Depending on if n is even or odd, this is going to alternate. And so it's an alternating harmonic. And we know that an alternating harmonic converges. And so what that means is we are going to include the 7 in our interval. So we would say that x is between 3 and 7, but it includes 7. And so all of that work altogether would be one part of a free response, like a part A or part B or something, but it would be worth some 4 to 5 points. And a good amount of those points are coming from checking the endpoints. Probably 2 points coming from checking the endpoints and 2 points from actually performing the ratio test and solving and so on. All right, so let's try another one. So we already said the radius of convergence was 2, and we already had our interval of convergence between 3 and 7. All right, so try this one. First of all, we need to decide where is it centered. Well, because it's just an x, it's not an x minus 2 or anything like that. It's going to be centered at 0. Okay, so file that away. Now we set up our ratio test, the n plus 1 term compared to the n term. And remember, to find the n plus 1 term, you're just putting in an n plus 1 in place of every n that you saw up here in the original series. And I didn't say this last time, and I should have, but notice I'm not putting the negative 1 to the n in as a part of the ratio test because I have absolute value. I mean, I could put it in there, but if I have absolute value, isn't that going to make it be positive no matter what? So I'm not going to worry about it so that I don't have to kind of clutter this up and make it look ugly. So first thing I'm going to do is I'm going to simplify, right? I'm going to distribute the 2, add the 1. So really what I have down there is a 2n plus 3 factorial. And I'll do the same thing on the top. So really what I have up there is x to the 2n plus 3. Remember, that's just the exponent on the x. And so if I simplify the 2n plus 1 factorial over the 2n plus 3 factorial, that's going to leave me this 2n plus 3 and the 2n plus 2. And if I simplify the x's, x to the 2n plus 1 on the bottom, x to the 2n plus 3 on the top, well, doesn't that mean I have 2 more x's on top than I had on bottom? So that's an x squared. And so remember, we're doing the limit as n approaches infinity. So if I have 1 over infinity, even though it's being multiplied by x squared, isn't that just going to be 0? It's like going to be like 0 times x squared. So it doesn't matter what x is. There's no equation to solve. This limit equals 0. And since it is always 0, and 0 is always less than 1, that means this series converges all the time. All the time. So the interval is going to be from negative infinity to positive infinity. And we would say the radius of convergence is infinity, because forever to the right of the center and forever to the left of the center, we're going to have a converge. So we've done 2 examples. One was where our limit equaled a value, and we were able to find the radius of convergence to be a specific constant. One was where the limit equaled 0, in which case we knew that the radius of convergence was infinity. And so now we're going to do a third example. Again, first we decide where is this centered. You can tell it's centered at 3. And so now we set up the ratio test. And in this case, since the original series wasn't a fraction, I went ahead and wrote it as the n plus 1 term over the n term. And so now when I simplify, the n plus 1 factorial over n factorial is going to leave me with an n plus 1 on top. When I simplify my x minus 3 factors, it's going to leave me with an x minus 3 on top. And so this time, if I plug infinity in for n, I'm going to get infinity times x minus 3. Well, that's still just infinity. So no matter what x is, this limit equals infinity. The limit is always equal to infinity, and infinity is always greater than 1, which means this series is going to always diverge except at the center. So a series always converges at the center, but it might not have an interval. It might not go any further to the right or left than the center. So it diverges everywhere except at the center. So this was an example of when the radius of convergence was 0. So it didn't move to the left or the right of the center. So it only converges at the center. In this case, it was x equals 3. Okay, so that's a little bit about interval of convergence using the ratio test and or the geometric test.